No way.
I got both, but I didn't really go from like huge special so I it's like they just visualization of computer science which can take around courses.
Okay, folks. Very, very good. So I'm glad people did a bit of exploring there. Yes, you want to, during those breaks, you want to explore, check out the textbook, try and make your own sense of the stuff. Try and, figure out things for yourself. Or figure out things for your friends. That's even better. Okay, so for this motion relative to center, do we have any guesses, thoughts? Guesses, thoughts? Yeah, sure. Yeah. Yes. Nice. Yes. So it is a circular motion, right? Yes. It's totally circular. So this is a circle. Okay. So we're parameterizing the position on a circle. And what was the parameterization you gave? Negative r cos t, negative r sine t. Okay, so I like it. I want to check if it matches this picture. Okay, so we'll take a moment. We'll see, does this line up with the picture that we have? Okay, so if we put in t equals 0, we get negative r 0. Does that match the picture that this vector is pointing downwards?
If you started with the point that we define, I guess, as 0, 0, at the leftmost point on the circle, could you write it as cosine sine?
Yes. Yes. So yes, there are if you move this starting position, you can get different curves. Or sorry. If you move this starting position, you can get different equations. Yes. I want to get something that matches what we drew the first time. Just so we're all on the same page with this one. Yes. What's the fix?
Well, you can do negative sine or sine cosine.
Right. So this does not match exactly what we have drawn, but it's very, very close. So if we fix this with a sine here and a cos here, then when we plug in, right, r sine 0 gives us 0. R cos 0 gives us negative r. The thing is pointing downwards as we expected, and now it matches. Okay. A lot of this stuff is guess and check, right? It's hard to think of this stuff the first time. So when you come up with a guess, you should check it against the diagram that you have, and you will often have to make a small correction. But this is a good suggestion. So, so let's put them together now. We've got motion relative to center. We've got center relative to the ground. Right, so what we're doing is we take the position of our center and we add the motion relative to the center. Okay, this is addition of vectors. So we take a vector that points to the center and then center relative to the thing. So we get here, we add these two as vectors. Okay. We get a formula for the position of this guy. Okay. And it seems to match with the book. Very good. And we can also play around with this. So let's make this thing of radius 3. That seems to line up pretty well with the sort of shape of the thing. Looks pretty good compared to this cycle. an example of a curve that it is natural to get a parametric version of, right? We got our parametric version by describing it in terms of two simple parts. Each part we can understand physically what's going on. It's not clear how we could get a Cartesian version of this right off the bat, right? It's not, you'd start with like x squared plus y squared is 1, and then, actually I have no idea what you would do after that. So this is nice in that it's a physical motion that can be better described with parametric equations than Cartesian equations. Okay. Great, so I want to come back to this notion of calculus with parametric equations. I want to do some kind of integration. We talked about finding derivatives, but we didn't talk about finding integrals yet. So we'll try an integration. So integration usually represents this process of finding the area under a curve. Okay, so this is the area under y from x equals a to x equals b. Just to say where we are in our book again, we're now headed back to calculus. And we're now on integrals involving parametric equations. And hey, look, there's our friend the cycloid. Okay. So, what we'll do is we'll answer that question that Galileo asked, which is how much area is underneath an arc of a cycloid? So Galileo answered this question by making a cycloid with a physical wheel, cutting the thing out of metal, weighing it, which is like a super duper hardcore way to do a calculation. But yeah, let's see what we can do to calculate out that sort of thing. So we've got a parameterization of the cycloid. Okay. And now the question becomes, how on earth do we use this notion of integration, right, with parametric stuff? Right? What do we do with this y dy in order to calculate the area under this curve? Okay. Answer is we substitute in x and y into that equation. directly substitute into the integral. Right? One arc of the cycloid, our bounds are 0 and 2 pi. Okay, so we plug this guy in. See some people who are like, what? This is really weird, right? We substituted in for x. Like, in the dx part. What? Right, so we just plugged it in. So what do we have to do to make sense of this expression? Well, what we want is we want to get something dt at the end. Right? Our goal would be to have integral, integral, integral dt. And then we could know what to do. Okay. This is reasonable. This is a reasonable derivative. So far, so good. So what we're going to do is we're going to say